Hola, Suhai Earth Science students. This is Mr. McLeod again. Welcome to our next astronomy podcast on the night sky and constellations. Today we'll begin our discussion of the motions of stars, star formations and planets, and eventually end up showing you how to locate certain constellations in the coming summer sky. One of the things you can do for yourself right now in this vein is to find a clear night and find the Big Dipper. Sounds easy, sometimes it's not. So if you have any questions about it, please ask, but it's a great place to start in our night sky right now. Find the Big Dipper. Honestly, this may be the most useful thing we do in this unit because it's something you can learn and teach others. So get your notes out, something to write with, and let's explore the night sky. Now, here's a great picture that you see right here of the motion of the stars in our night sky over the course of a night. Now, can you guess what the center point of this picture is? This point right here? If you said it's Polaris, you'd be correct. Remember, Polaris is our North Star. Because the Earth's north axis points to Polaris, all the other stars appear to rotate around it. Write that down. Now, it's really important to remember that when we talk about the sun moving in our sky, this is a misconception. The sun doesn't move at all. The sun's in a relatively fixed position. The sun looks like it's moving in the sky daily because of the rotation of the Earth and because of its revolution around the sun. When we refer to the sun's motion, we call it the sun's apparent motion, not its actual motion. What this means is that the sun appears to move in the sky, but it's actually not. Write that down in your notes. So from now on, when we refer to the motion of stars, we're talking about their apparent motion and not their actual motion. Now, the stars do move. Can you remember how? If you said that all stars rotate around the center hub of our galaxy, the core, you'd be correct. Now, the reason we don't feel their motion is that it takes a long time for them to make one rotation around that core. So we're not really moving fast enough for us to feel it. We can definitely see their motion by tracking individual stars night to night, week to week, month to month, and so on. Okay, let's move on. Like all objects in the sky, the stars, including our sun, rise in the east at an angle of 50 degrees with the horizon, move across the sky, and set in the west. Now, this ordinary motion that we see every clear night is known as daily or diurnal motion, D-I-U-R-N-A-L. Write that in your notes. Again, we're exploring how stars move in our sky. First, let's find something called the North Celestial Pole. You'll see it right here. The North Celestial Pole. It's here on this diagram, and it's right here, but not all the way through this diagram. So you see the North Celestial Pole. The stars appear to rotate around the North Celestial Pole, which is really the Earth's axis of rotation projected out into space. Write that down. So the North Celestial Pole is the Earth's axis of rotation projected out into space. Now let's also find the celestial prime meridian. So you see it here, the celestial prime meridian on the right and on the left. So here's the celestial prime meridian. Excuse me. And here's it drawn out for you right here. the prime meridian. Much like the prime meridian on our Earth, we just call this the celestial prime meridian. As we discussed earlier, the Earth rotates on its axis in about 23 hours and 56 minutes. Write that down. So it takes 23 hours and 56 minutes for the Earth to rotate on its axis. Remember, that causes day and night. However, the Earth must travel 1 degree further in its orbit, remember revolution, in its orbit for the sun to appear to travel from the meridian back to the meridian where it started. So, in order for it to go from here all the way around and back to here, the Earth needs to move 1 degree further in its orbit. Write that down. So it takes 23 hours, 56 minutes for the Earth to rotate on its axis. However, it needs to move 1 degree further in order to move from the start, from its start at the celestial equator back to the beginning. Now this extra 1 degree of travel takes an additional 4 minutes each day. Takes an additional 4 minutes each day. So get that in your notes. Now, 1 day by the stars, meaning 23 hours and 56 minutes, is referred to as the sidereal day. And you see it written up here. The sidereal day. 23 hours, 56 minutes is the sidereal day. However, this orbit path that it takes on the celestial prime meridian takes 24 hours. That's called the solar day. Sidereal day, 23 hours, 56 minutes. Solar day, 24 hours. So what I want you to know is the difference between a solar day and a sidereal day from a time standpoint, meaning a solar day is 24 hours and a sidereal day is 23 hours, 56 minutes. But more importantly is why they must be different. They've got to be different in order for the sun to appear to travel back to its starting place on the celestial prime meridian. Write that down. Here's a really good visual example of how the sun moves in our sky during the year. Now, if you can view the eastern horizon from where you live, you can track the sun yourself, much like in this picture. For example, when we look out my back window, we're looking straight at the eastern horizon. If we would track the sun during the year, we could see it move just like it's moving here. So let's try and make some sense of these pictures. Remember, we're looking at the eastern horizon in all three of these pictures. Now we know that because the sun's rising. You can see it rising in these pictures. So the sun's starting here and it's moving up here. It's moving up, rising. So that's got to be the east because the sun rises in the east and sets in the west. So to the left is north. So this way is north. And to the right is south. Okay, now let's look at the middle picture first. That's this picture right here. Now, can you guess what time of the year or what position the sun is in this middle picture? If you guessed the equinoxes, you'd be correct. On the equinoxes, meaning the autumnal September 21st, or the spring or vernal on March 21st, the sun rises due east, spends 12 hours above the horizon, and sets due west. Write that in your notes. Next, let's look at the bottom picture. So now we're looking at this bottom picture. Can you predict the date and position of the sun in this picture? Remember, north is to the left, south is to the right. If you said the date was December 21st and the sun was as far south as it can get, you get a gold star, just like our sun. So write in your notes that in the winter, the sun rises far to the south of east, spends as few as 8 or 9 hours above the horizon, and sets far to the south of west. So write that in your notes. Okay, now the top picture. Well, you can probably predict the date and sun's position, correct? Remember, left is north, right is south. If you said it's June 21st and that the sun is as far north as it can go, well, you'd be correct. Now write in your notes that in the summer the sun rises far to the north of east, spends as much as 18 hours above the horizon, and sets far to the north of west. So get that in your notes. Okay, now just a bit more on the motions of the moon relative to the sun and the earth. Remember, we're talking about the night sky now, and we've gone over star motion in general, and now we've got to finish up moon motion. You can make 4 observations if you watch the moon move through the sky over several months. Some you probably know, others you may not. First, the apparent size of the full moon varies from month to month, and from different sizes of the full moon, we can conclude that the moon's orbit is quite elliptical. Write that down. So the apparent size of the full moon varies from month to month for sure. And from the different sizes of these full moons, we can conclude that the moon's orbit is quite elliptical. So get those 2 things down. In fact, it varies by 13.3% of the average distance. Perigee, our closest approach, is 356,000 kilometers. Apogee, our farthest approach, is 407,000 kilometers. Write that down. The second observation is something you already know, but is worth mentioning again. Remember, the moon doesn't orbit the Earth on the ecliptic. The ecliptic is the plane of the Earth's orbit, an apparent path of the sun against the background of stars. But rather, the moon spends half of its time above and half of its time below the ecliptic, like we see here in this familiar diagram. From this, we can conclude that the moon's orbit is tilted or inclined 5 degrees with respect to the ecliptic. Now later, we'll use the inclination of the moon's orbit as a clue to its origin. Write down that the tilt is evidence that the moon was not formed at the same time as the Earth, nor was it formed in the same region of space. So write those 2 things down. Tilt is evidence that the moon was not formed at the same time, nor was it formed in the same region of space as the Earth. Okay, observation number 3. The moon moves eastward against the background of stars. Write that down. The moon moves eastward against the background of stars. Now, this causes the moon to lag behind the stars, rising 53 minutes later every evening. Now, I know you've written that down, but I want you to write it down again because it's responsible for the difference in timing between the sun and the moon's movement. So the orbital motion results in the changing lunar phases. Again, something you learned when we studied the moon phases, but it's just worth mentioning again. Now, the fourth observation is that the same side of the moon always faces the Earth. This means that the moon rotates on its axis at exactly the same rate which it orbits the Earth. We call this locked rotation synchronous rotation. synchronous. Synchronous rotation. Write that down. Now let's take a look again at what this looks like. So the rotation period of the moon is exactly the same as its period of revolution. Look at the red shading and you'll see that we never see anything but the red shading in this situation. It's because of synchronous rotation. Okay, now let's switch our focus to the movement of the planets in our solar system. Like all objects, the planets rise on the eastern horizon and set in the west due to the Earth's rotation. Get that in your notes. However, like the moon, the planets usually move eastward against the background of the stars. Write that down. The planets move eastward against the background of the stars, like our sun. Now, how fast they move depends on their distance from the Earth and their orbital distance from the sun. Write that in your notes as well. So how fast they move depends on how far away they are from the Earth and their orbital distance from the sun. So write that down. We call the normal everyday movement of planets eastward their prograde motion. You can see up in the upper left-hand corner, prograde motion. That's the everyday normal movement of planets eastward. Write that down. However, once or more each year, the planets do something very strange. They pause in their normal eastward or prograde motion and begin moving westward for a few weeks. We call this movement their retrograde motion. See the word retrograde in the upper right-hand corner. We call that their retrograde motion. So make sure you get that in your notes. They begin moving westward for a few weeks. We call this their retrograde motion. And you see a really good example of it here. Take a look at this picture, and it shows Mars going through its retrograde motion. Kind of loops back around, sort of like travels backwards. Once this retrograde motion is over, the planets then resume their normal eastward prograde motion. More than any other motion of objects in space, this retrograde motion of the planets confused the ancient people and seriously affected the development of astronomy as a science. Retrograde motions arise from the combined motions of the planets and the Earth. Write that down. Copernicus was the first to explain this motion. He reasoned that planets further away from the sun would move more slowly than the closer ones, so that as a faster planet overtakes the Earth in their rotation, its motion against the stars, as seen from the Earth, reverses. Write that down. So planets further away from the sun move more slowly, so that they overtake the Earth in their rotation. And its motion against the stars is seen from the Earth as reversing. Write that down. Look, for example, at this simulation. As we view the faster moving Venus from the more slowly moving Earth, here we got Venus and Earth here. As we view the faster moving Venus from the slower moving Earth, the line of sight, what we mean by that is where in the sky, relative to the stars, we see Venus, reverses its motion. It's first rotating counterclockwise, then starts rotating clockwise. This corresponds to the first reversal of apparent motion. Now, a while later, it starts rotating again in a counterclockwise direction. This same explanation works for outer planets too, only now it's the Earth that overtakes the outer planet. So this causes retrograde motion. Take a look at this, and you can see why it happens. It's that speed difference between Venus and Earth. There goes Venus right past Earth. As it goes past Earth, it looks like it's going backwards. Think of yourself passing a car and you got the same situation. If you're the car doing the passing, it looks like the car you're passing is going backwards when you pass it. Same situation here with retrograde motion. Okay, that's it for part 2. Go grab those questions on Moodle, answer them, and submit them when you get done. And we'll see you again for part 3. Bye.